All right, so this is the question we gave, right? So we want to show that this one is divergent, right? So but we have a relationship between Cauchy and convergent, right? So in the last theorem we studied in the last class, we proved that if the series is Cauchy, then it is convergent, right? So and so suppose we assume that the sequence is Cauchy, right? So you know that actually the results is for every epsilon positive there exists n belongs to natural number such that summation of k running from n plus 1 to m 1 upon k absolute value is less than epsilon for all m bigger than n bigger than n. That is what we write as a Cauchy condition, right? But here what we do is we choose epsilon is 1 over 4, right? Because the result is true for all epsilon. So you can choose whatever the epsilon you want. So here in this case, we choose 1 over 4, right? So later on you will figure out why we choose 1 upon 4, right? We could have choose it 1, we could have choose it half, we could have choose it as any number, right? Even 100, it is fine. But the reason why we choose it 1/4, you will understand later, right? So let me show you this. So this is the condition, right? So what you do is you choose m is equal to 2n, right? So actually if you choose this, then what you have from here is and so k running from capital N plus 1, right? So for any n bigger than n, the result is true. So you choose n as capital N, right? So then you have n plus 1 up to 2n is less than 1 upon 4. So you can write it down, right? Right, so you have 1 upon n plus 1 less than plus 1 upon n plus 2 plus all the way up to 1 upon 2n is less than 1 upon 4, right? But you know that 1 upon n plus 1 is bigger than 1 upon 2n, right? Right? But 1 upon 2n, because 2n is bigger than n plus 1, 2n is bigger than n plus 2, 2n is bigger than n plus 3, and 2n is obviously bigger than 2n minus 1, right? So all those numbers, 2n is bigger than that. So when you take 1 upon 2n, that is smaller than 1 upon n plus 1, 1 upon 2n is smaller than 1 upon n plus 2, and so on, right? So because of this result, all these, when you replace by 1 upon 2m, still hold, right? right? So when you replace it, all of them are less than n plus 1. 1 upon 2n is less than 1 upon n plus 1. Another 1 upon 2n is less than 1 upon n plus 2, and so all the way. So eventually 1 upon 2n plus 1 upon 2n plus 1 upon 2n is less than 1 upon 4, right? According to this inequality, right? Now there are n plus 1, n plus 2 up to 2n. So there are n terms there, right? You understand that? There are n terms there. So here are n terms. When you add all of them, you get n times 1 upon 2n. Right? When you add n times 2n, you get 1 upon n times 1 upon 2n. Right? So that's basically, so this case 1 upon 2 is less than 1 upon 4. Correct? Right? So that's not true. You all know that, right? 1 upon 2 cannot be smaller than 1 upon 4. Right? So this is basically a contradiction. Right? So this is why you choose 1 upon 4. Right? So suppose you choose it as 1, right? Then you don't get contradiction here. Right? So the idea of choosing 1 upon 4 is you want to choose something smaller than 1 upon 2. Right? So then only you get the contradiction, because the result is true for all epsilon. You are free to choose any number as epsilon. So you can always, by looking at this idea, you understand that as long as you choose any number smaller than 1 upon 2, you will get contradiction, right? So even in place of 1 upon 4, if you choose 1 upon 8, you still get contradiction, right? So 1 upon 4 is not the only value, but you have to choose something smaller than 1 upon 2. Right. So now, because this is a contradiction, this is not true. If this is not true, the series is not Cauchy, right? So right, so the series is not Cauchy. If the series is not Cauchy, then you know by previous results, not convergent, right? So not convergent means divergent. Okay, so that's how you use the Cauchy criterion to verify whether a series is converging or diverging, right? So if you prove the series is Cauchy, then you can show that the series is convergent. If you prove the series is not Cauchy, then you can say that the series is divergent. And so that's the application of the Cauchy criterion we studied in the last class. So now let us move on. A little bit more on the convergence of series. Right? Couple of classes before we studied this result. Right? So this theorem, I write it down. So this is one of the theorem we studied earlier. Right? If the series is convergent, then we prove that the nth term, right, in the series un will converge to 0 as n tends to infinity. Right? So if the series is convergent, then the nth term will goes to 0. Right? But converse is not true. But the converse of this statement is not true, right? The example is here, right? That is and so even if the nth term okay, even if the nth term is converging to 0, it is not necessary that the sequence, sorry, the series is convergent, right? Counter example. Whenever you try to disprove something, or whenever you try to prove that something is not true, right? So you always, it is easy in most of the cases to give a counter example. So here we will give a counter example, right? Right, so this is the very easy counter example because we already proved this result. Here we prove that 1 upon n summation is not converging, it is divergent, right? But in the sequence chapter 2, we prove that 1 upon n converges to 0 as n goes to infinity. So here is the example, right? So n term 1 upon n is going to 0, but the series is not convergent. So that is why we say that the converse of the theorem we studied earlier is not true, right? So then how we can modify these results, right, to see convergent, right? So this result is about if convergent, then something happens. But what we want is we want to see convergent, right? So that is the important part for us in this course, right? We always try to prove whether the sequences, or try to see whether the series is convergent or not. So this result is not going to help us much, right? Because you hardly see the convergent, right? Because if it is convergent only, the other results is true. So we will try to modify this theorem a little bit to get the results that help us to see the convergence of the sequence. Right. So okay, so let me write the theorem. It is something like a monotone convergence theorem you studied, right? So it is analogy. Right, so it is very similar type to the monotone convergence theorem you studied in the sequence, right? So in the sequence, you see that monotone sequence that is bounded converges, right? So that is the monotone convergence theorem you studied, right? Monotonicity and boundedness together guarantees the convergence, right? So monotone increasing bounded above, or monotone decreasing bounded below, or both ways, right? So it guarantees the convergence. So we are trying to develop a similar kind of results for the convergence of series here, right? Boundedness and monotonicity, we try to create a relationship. Right? So let's say so the first thing is all the terms un are positive, right? Positive means non-negative, greater or equal to 0, right? For all n belongs to natural number. So that's the first condition you need to check, right? Then if the sequence of partial sum is bounded, then, right, then the series is converging. If the series is convergent, then the partial sum is bounded, right? So that is the results we have, right? So first thing is for both the results to hold, you should have the terms to be positive, right? So that's a important thing. Okay. So because un is positive, sorry, non-negative for all n, right? The proof is not a big thing, it's very simple. Right? Because you know the meaning of partial sum, right? The partial sum means you keep on adding terms, right? First term, then first and second term, first, second, third, first, second, third, fourth, right? So by adding that, you are creating a sequence, right? So that is the sequence Sn known as the partial sum, right? So because all the terms are greater or equal to 0, when you add the term, the sequence is obviously increasing, right? So you can easily understand that because the terms are positive or non-negative and greater or equal to 0. So the terms, when you keep on adding, the sequence will get bigger and bigger and bigger, right? So it is monotonically increasing sequence. So monotonically increasing sequence, you know that this result is true. Bounded if and only if convergence is the results you have as the monotone convergence theorem, right? In the sequences. In the sequences, you study that monotone convergence theorem. Monotone sequence is convergent if and only if it is bounded. But the sequence of partial sum is convergent is equivalent to, right? But in the series you studied, the series is convergent is basically equivalent to partial sum. Sequence of partial sum is converging. Right? So if you combine both of them, you see that so clearly the series is convergent if and only if the sequence of partial sums is bounded. And so that's the results we have. Okay. So now we have studied about convergence of series, right? And relationship between the convergence and the Cauchy, relationship between convergence and boundedness of the sequence of partial sums and all the other things. Right? So now what we are going to do is we are going to move on and try to develop some tests, right, that will help us to justify the convergence of the series. Right? We will try to develop some tests, right? And by applying those tests, we will try to develop the convergence conditions, or we will try to verify whether the sequence is convergent or not by applying the test. Right? In order to start that, let us start with the well-known, very well-known series, right, which is known as P series. So in order to start this test, right, so let us define something called P series first, right? So P series will be of the form here. P series will be of the form 1 upon n to the power p. And P series is a series that is of the form summation of 1 upon n to the power p. Here, p is a number bigger than 0 and less or equal to 1. Right? P be any number between 0 and 1, right? Strictly bigger than. Strictly bigger than 0, right? Because equal to 0 does not make sense. And strictly bigger than 0, right? And the between 0 and 1, right? This is clear for you. Okay. For any p between 0 and 1, and for any n to the power p is less or equal to n. You know that, right? So because p is the power between 0 and 1. So if it is equal to 1, n is equal to n. If it is less than 1, then obviously n to the power p is smaller than n. Right? So if you invert them, right, then clearly 1 upon n is less or equal to 1 upon n to the power p, right? And this, right? Okay, so you have this P series. First, we take, right, this case, right? P series is actually of the form this, right? And so we take this case. Let me say case 1 in the base P series, right? So that then you can easily understand. Because next I will talk about what will happen when P is bigger than 1. Right? So here we are talking about the case P series n to the power p, p between 0 and 1. Right? So in that case, you can understand that 1 upon n is less or equal to 1 upon n to the power p. Right? But This is very obvious for you again. Summation of 1 upon n, and you take the partial sum, right? That partial sum is not bounded because you keep on adding numbers. The sequence of partial sums of 1 upon n is not bounded, right? I believe we did something like this exercise as an exercise in the sequence as well, right? The sequence given by 1 plus 1 upon 2 plus all the way up to 1 upon n is not bounded. And so that's what we are doing. The partial sum is not bounded. So if the partial sum is not bounded, or partial sum of this is not bounded, obviously this one is bigger, right? So if the partial sum, the finite sum of this is the sequence of finite sum of this one is not bounded, when you take the partial sum of this series, and obviously you know that is also not bounded because the smaller one is not bounded, so obviously the bigger one is also not bounded, right? And so you can easily verify that because the partial sum of summation of 1 upon n is not bounded, 1 upon n to the power p is bigger, so that partial sum is also not bounded. If partial sum is not bounded, what is the theorem we studied earlier, right? Analogy to the monotone convergence theorem, right? Convergence if and only if partial sum bounded. So here partial sum not bounded, so not convergent. So for these values of p, the p series diverges. And so you see that the p series diverges for p between 0 and 1 equal to 1 also same. And because equal to 1 is 1 upon n, and you know that that one is divergent already. So here in case 1 of the p series, right? So generally the p series is of the form like this, summation of 1 upon n to the power p. In that you take the first case where p is between 0 and 1, right? And then we see that for that case the p series is diverging, right? P series is not converging. So that part is over. Now we will focus on what will happen when p is bigger than 1, right? So in that case the series will converge. So let us write that as a theorem. Okay, so the series is converging if and only if p is bigger than 1, right? P series is converging. So that's basically the second case, right? So you understand that now. The second case, p bigger than 1 case, the series is convergent, and the vice versa is also true, right? So the converse is also true. If the series is convergent, then obviously p must be bigger than 1, right? So we will prove this results. This is a slightly bigger proof, right? So I'm going to it's a big proof, so let me give you the hints of how to do that, right? The proof. Let us suppose that p is bigger than 1, right? So in this case, we want to show that the series is convergent, right? So you want to show that the series is convergent. And so if you want to show the series is convergent, then you know you have to find the partial sum. So let me define Sn be my partial sum. right? So this is my partial sum Sn, right? The partial sum Sn is summation of k to the power 1 upon k to the power p with k running from 1 to n. Right. This is what you want to show, right? So you want to show this is bounded, but showing that this sequence is bounded is slightly difficult. So what we are going to do is we are trying to develop a subsequence, right? Because we already studied about subsequence in chapter 2. So we are going to use that results here, right? So instead of showing that the sequence is bounded, we will try to show that this sequence has a bounded subsequence, right? So we are trying to show that this sequence has a bounded subsequence, right? So this is what we are trying to show, right? The subsequence of the sequence Sn is bounded. So that subsequence we take it as S2 to the power n, right? As the indices are 2 to the power n, right? So in place of n, you choose only the terms in the form 2 to the power n. That means 2 square, 2 to the power 3, 2 to the power 4, only those terms, right? So that means 1 upon 2, 1 upon 4, 1 upon 8, right? Those are the terms. 1 upon 2 to the power p, 1 upon 4 to the power p, 1 upon 8 to the power p. Those are the terms we are trying to show. Okay. So we are trying to show that the subsequence 1 upon s to the s2 and 2 to the power n is bounded above, right? So in order to show that, we will try to show these two results, right? S2 to the power n plus 1 minus 1 is less or equal to s 2 to the power n minus 1 minus 1 plus 2 to the power. And so first result, let me show you how to do that. So you try to find this. And so you try to find this s to the power 2n plus 1 minus 1 and this. So this is actually, you can first 2 to the power n, yeah. N minus 1. This is easy. First you try to find these two, this, right? So that means you will get this. Summation of okay, so if you write down the partial sum, right? Partial sum is 2n 2 to the power n plus 1 minus 1 is k running from 1 to p, this minus this, right? So k1 2 3 4, here also k1 2 3 4. So here all the way up to 2 to the power n minus 2 to the power n minus 1 will be cancelled out, right? Because here also when you put k1 cancelled out, k is equal to 2, 2 cancelled out, 3 cancelled out, because 2 to the power n plus 1 is smaller than 2 to the power n plus 1 minus 1. You all know that, right? So eventually all the terms here got cancelled out, right? Here, right? So the rest is what you have. So if you write it down, you get this. Because 1 upon 2 to the power n minus 1 will cancel out, but get cancelled out. So the next term is 1 upon 2 to the power n, right? And then 1 upon 2 to the power n plus 1, 1 upon 2 to the power n plus 2, right? And then all the way up to 1 upon 2 to the power n plus 1, right? So this is what you have. What I'm going to do is I'm going to stop at this moment because we are running out of time, right? So first, you check whether this statement is right or wrong, right? By writing everything out and cancelling out, right? As a homework, and then you try to see whether you will be able to get these results from here, right? If not, I will continue the rest in tomorrow's class, right? So that is where we are going to stop here. You try to check whatever the work we did already in this theorem, and from tomorrow's class I will start from here on, right? So you check whether up to here everything is correct or not, right? So let me stop here and then continue tomorrow at 1.